Okay, hello everyone. Welcome to today's session, module 12, IPv6 addressing. So the last session that we did, the last module that we did, we discussed IPv4. That is the last module that we did. We introduced the IPv4 address, 32 bits. We talked about the network ID. That is the host portion and the host portion and the network portion of the IP address. We talked about the subnet mask. We talked about classes of IP addresses that we have. We also discussed the range of those classes. Then what else? I think lastly we talked about subnetting, the need for subnetting, breaking down a huge network into smaller segments. We did subnetting. Most importantly, variable length, using variable length subnetting mask. And basically that was it. Today we discuss IPv6 addressing. I think the overall objective of the IP addresses being to uniquely identify hosts in a network. So we have two types of those IP addresses. Version 4, which is IPv4, and version 6. Today we look at version 6. So what are we going to be looking at? Let me look at the objectives. The module objectives are to implement an IPv6 addressing scheme. We'll start by looking at issues that have led us to have IPv6. So we explain the need for IPv6 addressing. Why have version 6? Is version 4 not good enough? Then we'll look at explaining how the addresses are presented, the types of IPv6 addresses that we have, mainly those two, GUA and LLA IPv6 addresses. We look at how they are configured, which is pretty much the same way how IPv4 addresses are configured on hosts. We'll also look at dynamic addressing of GUAs and LLAs, global unicast addresses, and link local addresses. We also look at the multicast addresses. We have quite a number of different types of multicast addresses. We'll discuss those. Then lastly, look at subnetting an IPv6 network, which is not as complex as with the IPv4. This one is very much easy. One of the reasons why we now have IPv6 version 6 and not only version 4. Right, we start with the need for IPv6. Why? Why have IPv6? So we have IPv4 is running out of addresses. IPv6 is the successor. IPv6 is much larger address space. The development of IPv6 also included fixes for limitations in version 4. We'll discuss those limitations. Lastly, with an increase in internet population, a limited version 4 address space, issues with NAT and IoT, the time has come to begin the transition to IPv6. Right, so reasons why. Why do we need IPv6? So basically, number one, the major reason is without version 6, the world was running out of IPv4 addresses. With IPv4 addresses, I think we discussed the total number of addresses that we have. I think the last time we discussed it, we just said 2 to the power of 32. Uh, it was millions, I think. I'm forgetting this number. Quick calculation. Let me do a quick calculation. Who has that number in his head? Is it 2 to the power of 32? It should be 4 million. No, no, no. 2 to the power of, let's try 2 to the power of 24. 16 million. 16 million. I have 2 to the power of 24, which is 16 million. Let's just say 16.7 million. right? The number of addresses that we can have using a slash 8, using a slash 8 network ID. So we can have 16.7 million addresses. And if we look at our population right now, I think 8 billion, almost everyone having almost everyone having a cell phone, a laptop, all those things needing my IP addresses, meaning 16 million addresses, host addresses, unique host addresses is no longer enough. 16 million is no longer enough. Although we have, for example, technologies like NAT, which allows us to uh, preserve and save some of these addresses, but 16 million is not a huge number. Another reason, we have the introduction of IoT. IoT, Internet of Things. Almost every device in our households has an IP address. Our fridges, security cameras, with the introduction of smart homes, even motor vehicles, they now have IP addresses because they are connected to the internet. So basically, it means we are running out of space for IP addresses. With the introduction of IPv6, which has a total of 128 bits, 128 bits from 32. IPv4 in 32, IPv6 128. It pretty much means we have quite a lot of space now. Currently, I think we are using slash 64 with IPv6. Let me see how many addresses are those. 2 to the power of 64. That's a lot. I don't even know how to count this number right here. I don't know. Right, I'm thinking, don't mind the silence. I'm thinking, I don't know how to count this number, but it's 1.8 times 10 to the power of 19. That's a lot. Kuzoona tapedza ma-addresses, I don't know. That's a lot. And we haven't used my bits ASRapa. We have only used 64 bits from the host portion, here version 6 address. So you can see moving from version 4 to version 6 already solves the problem in address space. And that was one of the problems dzanga dziripo. So from the diagram up, you can see, I think let me just introduce from the diagram, you can see, pana tinoti ma regional registries, RI, IRAS, my IP address, where do they come from? Regional internet registries. Where do IP addresses come from? We have an organization. I think we introduced that organization. This one. This one is responsible for assigning, uh, controlling. I can't find the right word. Controlling, managing assignment IP addresses. Right? After they've done that, they leave it to the regional internet registries. Do ayarapa. Arin, this is RIPE, this is APNIC, this is Afrinic, this is ours for Africa, this is LACNIC, 5 of them. Then these 5 RIRs ndo anozoasaina kuma service providers edu. I think we are familiar with service providers edu kuno. And I tell one, ndo anozoasaina. Then my service providers, they assign to organizations or homes, whatever it is. Then from organizations, manetwork admin oita basa rawo ndo panotangira musubneta network yamunenge mapiwa panapa. Mukasubneta mako assignawo manetworks enyu amunoda ndo pamunotangira panapa. But kwaabva from this organization to this one. Why I'm introducing this, from the diagram, you can see this one is already exhausted my version 4 addresses which were assigned to that region. This one exhausted, this one exhausted, this one exhausted. Ayakazopera zvawa. Projected exhaustion date 2020. Akazopera. Right? Afrinic. And the reasons why akanonoka kupera, I think we know. Right. Then what other reasons need for IPv6? We talked of IoT. With the introduction of IoT, I think I once read IoT was projected to have around 5 billion IoT devices. I think it was by 2020, 5 billion. So meaning we needed 5 billion IP addresses basically. So with the introduction of IoT, there is definitely need of having much more addressing space. Right, other reasons, we'll look at them, but think kuzofamba IPv6, mainly simplified header. Header, we discussed, we now know what the header is, we now know what the trailer is. We now know what fields are there in the IP header. So with the IPv6, it has a simplified header. Some of the fields that were there per IPv4, they are no longer there per IPv6, meaning it has less overhead. It's much easier to do routing using IPv6. Those are some of the reasons why we now have IPv6. Also, with IPv6, we no longer have need for NAT. NAT inema problems ayo, network address translation, inema problems ayo. For example, in troubleshooting, it's very difficult knowing kuti problem iri papi because my addresses that are being translated to public IP addresses, basically private IP addresses, they are being translated to public IP addresses. That translation leads to some confusion. For example, if you want to troubleshoot, what are you exactly troubleshooting? The network that you are seeing from the public, or the host that you are seeing that actually has a problem from the private perspective. So with IPv6, we eliminate the need for NAT. Therefore, that is the reason as well why we are now accommodating IPv6. Other reasons have to do with what we call Slack. We'll look at this auto configuration. So with IPv6, a host has the ability of assigning an IP address to itself. With IPv4, it's either you manually assign an IP address that is static, or is dynamic using DHCP, right? That is for IPv4. That's how we assign my IP addresses. With IPv6, yes, you can manually configure it, or you can as well use DHCP, but there is another option where a device, by communicating with the router, it can automatically configure an IP address to itself without these two ways. So without having a server, without having an administrator, for example, manually configuring the IP address. That is another advantage of IPv6, and we will later on discuss the process here at not Slack. All right. Lastly, in terms of security, IPv6 also offers more security. It has a number of features. Panyai authentication, it enhances its security with addition of some features which were not there by IPv4, which deals with authentication, basically improving security. Yeah, communication yedu. Right, so the need for IPv6, I think I've exhausted everything here. Right, coexistence. So you see, even if we want to use IPv4, it doesn't mean with the introduction of IPv6, we completely neglect the use of IPv4. We now have a coexistence between the two protocols, version 4 and version 6. How are they coexisting? One, we have what we call dual stack. the devices run both IPv4 and IPv6 protocol stacks simultaneously. So with dual stack, a network interface can be configured with both the IPv4 and the IPv6 addresses. I think, do we have a lab? I don't think we've done it yet, but you will see when we do a lab which consists of both IPv4 and IPv6, you actually configure both IP addresses on the same interface. So that is basically what we call dual stack, where both protocols exist simultaneously on an interface. Right, then we have tunneling, a method of transporting an IPv6 over an IPv4 network. The IPv6 is encapsulated inside an IPv4 packet. So tunneling enables IPv6 over IPv4 existing infrastructure. When we talk of encapsulation, so basically what happens is we have an IPv6 packet, then we add headers and trailers the IPv4, meaning this becomes the payload, the IPv6. So the data that we will be transmitting will be using version 4 infrastructure networks, but the actual data that we are transmitting is version 6. So basically that is what tunneling is. We encapsulate an IPv6 packet using IPv4 headers, and we transmit our IPv6 packet. Then we have translation, network address translation 64, not 64, which allows IPv6 enabled devices to communicate with IPv4 enabled devices using a translation technique similar to NAT for IPv4. Right, so with NAT 64, basically we are converting IPv6 to IPv4. However, tunneling and translation are for transitioning to native IPv6 and should only be used where needed. The goal should be native IPv6 communication from source to destination. So it's very not likely that you see these two being used, tunneling and translation. Why? Is either you are using IPv4 from source to destination, IPv6, or IPv4 from source to destination. Or you can use both of them. But if you want to transition from IPv4 to IPv6, then you just go and use your network using only IPv6, avoiding problems which come with, for example, this one, translation. There are issues that come with network address translation, which we would like to avoid. So it's either you transition from IPv4 entirely going to IPv6, or you use, this one is the one which is commonly used, dual stack. Right. And I think that's as far as coexistence goes. Let's look at the representation of IPv6 addresses. Right, so you see IPv6 addresses, they have 128 bits, as compared to IPv4, which is 32. So with version 4, 32 bits, version 6, 128. You can see the huge difference there. Okay, let me mute. All right. IPv6 addresses are not case sensitive and can be written in either lowercase or uppercase. Right, unlike here we use my numbers, but 32 bits is, we use my numbers. Where are we in Africa? 192.168.10.100 decimal. IPv6 uses hexadecimal. So with hexadecimal, we now know 0 to 9, A, B, to F. This is hexadecimal. So that is why you see letters, for example, A, B, C, D, because the representation uses hexadecimal. Right, so the preferred format for writing an IPv6 address is XXX. Okay, let me put it this way. So IPv6, it has 128 bits. Binary. This is binary. When we talk of 128 bits, this is binary. We want to go to hexadecimal. So from 128 bits divided by 4, what do we get? Divided by 4, we get 32. Because 4 bits, 0, 0, 0, 0, this is 0. 4 bits represents one hexadecimal number. Then 1, 1, 1, 1, this is F. 0 up to F. 4 bits represents one hexadecimal number. So with 128 bits, it means we have 32 hexadecimal numbers. I want to break down representation of the IPv6 address. 32 hexadecimal numbers. Then from those 32 hexadecimal numbers, they are grouped in 4s, like this one. This is a group of 4. So this is one hexadecimal number, another hexadecimal number, 3, 4 hexadecimal numbers here. So if we group them in 4s as well, we get 8. So we get 8 values separated by a colon. This thing right here. Right? So that's why we have, this is 1, 2, 3, 4, 5, 6, 7, 8. So what we have with IPv6, per number is, we have 128 bits, we've got 32 decimal numbers, 32 decimal numbers, 1, 2, 3, 4, 5, 6, 7, 8, 32. These are the 32 hexadecimal numbers. Then they are grouped in 8 groups of 4 hexadecimal numbers, forming 8 groups. Let me say 8 groups here. 8 groups of 4 hexadecimal numbers separated by a colon, and this is how the address is represented. As we go, tichaishortena zvedu pairi apa yakati kurei bichanapa. There are ways that we can shorten that IPv6 address. Right. In IPv6, a hex state is the unofficial term used to refer to a segment of 16 bits or 4 hexadecimal numbers. So in Indonesian hex state, I think the technical term, this one. So we are talking of 8 hex states make up an IPv6 address. Clear? Right. Address representation. Now, takuta shortening the IPv6 addresses. So we have ways of shortening addresses. Number 1, omitting the leading zeros. The first rule to help reduce the notation of the addresses is to omit any leading zeros. So for example, this is a leading zero. This is a leading zero to here. Is leading ish. So this is leading, Sara, 2 Sara. That's why we have AB. That's why we have A00 here, etc., etc. So that's how addresses are shortened. Right? This rule only applies to leading zeros, not trailing. So this one, it wasn't removed, this one, because it's trailing. Right? An example at a we can remove this one leading, this one, SR leading, 3IR leading, 3IR leading, 3IR leading, this one is leading. That's why we have 200 000 1110 TBH 2001. So that's how an address is shortened. All leading zeros can be removed from the IPv6 address. I think from binary, we know from binary, if I do this, this is 1. If I do this, this is 1 as well. I can remove these numbers. Those are leading zeros. But it's no longer the same. This is 4. This is 4. But in the end, I matrailing and gadai. This is no longer 4, that is 1. I think it's the same logic that is being used. So one way of reducing notation is by removing, omitting the leading 0. Another example, let's reduce, per example, ish. So let's deal with this one. So this one becomes 2001 db8. We've removed this one. Then we remove first 3 here. 0. 2 over A3, A, B, C, D. 3 over 3 over 1, 2, 3, 4. This is representation after omitting my zeros. Typical questions you getting in exam are exactly like this. You're going to copy your IP address like this one, and you are asked to reduce it. All right. Rule number 1, you omit leading zeros. Rule number 2. Rule number 2 says you can use a double colon. A double colon can replace any single this should be continuous, no? Continuous string of 1 or more 16 bits hextets consisting of all zeros. You can remove, a double colon can replace any single continuous string of 1 or more 16 bits hextets. So hextet 30 chi, hextet is 4 hexadecimal numbers. A hexadecimal, which is equal to 16 bits. So what they are saying, if you have a string of zeros, a hexatetrace 0, you can replace it with a double colon. So can only 1, 2, 3, 4. This can be replaced with a double colon. Can only a continuous string. For example, you can have 1, 2, 3, 4, 1, 2, 3, 4. This is a continuous string. 1, 2, 3, 4. It can be replaced by this. Right. Let's have an example and see exactly what we are talking of. Looking at example ish. Right. 2001 remains 0. If we apply rule number 1, anobo is 0. Those are on a db8. Right. Then panap, we have a tinema 0. A single hextet tinaro ir. This could have been replaced ne double colon. But however, a double colon can only be used once within an address. So unofanira kuchuza pari very wise kuriisa iroro. Tikarisa panapa, it's not wise. Why? Because we have a string irirape, continuous. So it's much wiser kuisa double colon papi pane continuous string iro. So panapa ndo pari kuyapo representwa ne double colon panapa instead of here. So panapa tichashandisa rule number 1 tobvisa 3 ma0. That's why we have a 0 here. Then pama 1 1 aripo akadaro. Then pane string iri ndo replacewa nechi nema double colon I. Then what we are left with is 200 irapo. So basically this is a compressed version yeaddress iri pamusoro iyi. Now tomboti unopiwa address iri apa, and you want to decompress this. How do you then decompress? It's very easy. You know, one, you know, ndiri kufanira kuita 8 mahextets. That's the starting point. That's the total number of hextets dzauri kufanira kuita paaddress. So breaking it down, panapa ndinoita 2001 ndotora icho db8 ndotora 0 uzvu 1 2 3 4 ndotora ma1 ayo 1 2 3 4. Then kwekupedzisira ndikuziva kuti ndinani, ndina 200. Ko double colon iyo, what is it representing? So if I count, I have 1 2 3 4 5 hextets, meaning my hextets asara mangani e3. So pakati apa, it means pane 3 my hextets continuous zeros. That's how you find the original IP address. You get a question, inogonotangira paaddress ishi. Yoda kuti ushandise reasoning yekuti udzoke panapa. And this is how you just use logic yekuti the total number of hextets dzandinofanira kuita mangani i8. So saka colony inoreplace. Hauudzwi kunzi yareplace mahextet mangani. But you should know kuti it replaces a single or a continuous string of zeros. And basically, that's how you come up with an address yakadai. Right, let's have another example. Let me go back. It's the same example. Okay, let's use this one. It's different. Let's use this example A to try to shorten with the two rules that we've learned so far. So 2001 remains as 2001. This one becomes DB8. Then we have single panap. Then we have two hextets upwards. So double colon yedu, it will be wiser panyaya dzecompression kuisa pane two mahextets aya. So pasina hextet apa, since tichikwanisa isa double colon ka1 once, we choose kuisa panapa. So panapa, rule number 1 takes over. Then panap we have A3, panap A, B, C, D. Then for this one, double colon yedu 1, 2, 3, 4. So this is how we shorten the version 6 address E rapai. Very simple. Very simple until mapinda exam. Let's continue. Omitting zeros, double colon, we've done that. Rule number 2. And basically, those are the two rules used to shorten an IPv6 address. Right. Let's move to address types. We have different types of IPv6 addresses that we have. Unicast. We now know what unicast is. One device sending to one device, one to one. Multicast, that is one to many. Send a single packet to multiple destinations. Anycast, this is a unicast address that can be assigned to multiple devices. A packet sent to an anycast address is routed to the nearest device having that address. Unlike IPv4, IPv6 does not have a broadcast. However, there is an all nodes multicast that essentially gives the same result. Right. I think I need to explain only these two for now. Even only this one, anycast. We know what a unicast is. We know what a multicast is. Tripa multicast ipapo, IPv4, IPv6, it does not have broadcast. Meaning in a network, broadcast, how broadcast basically works. If I send a broadcast, every address, every host in this network receives that packet with IPv4. With IPv6, we have what we call an all nodes multicast. So we have different types of multicasts. One to many, that is multicast. One type of a multicast is called an all nodes. An all nodes multicast allows us to send to every device on the local link. Then we have, for example, solicited node multicast address. This one is not sent to all like the all nodes. It is only sent to solicited nodes. It's another multicast address. So with IPv6, we don't have broadcast. That is very important. We don't have broadcast. The reason why we don't have broadcasts is because broadcasts, they are not efficient. They are not efficient. We'll explain the process here, neighbor discovery later on. I think takamboibata patakaita I'm not so sure which chapter where we were talking about neighbor solicitation and neighbor advertisements. I'm sure it will ARP. patakaita ARP module 9 takataura nezve-neighbor solicitation, neighbor advertisements, when we were discussing neighbor discovery, where we said in IPv4 we have ARP, in IPv6 we have ND. So later on, look at why broadcasts are not efficient. Because a broadcast sends to all devices. That's a lot of traffic. But with multicast, you don't have to send to all devices if you are using solicited nodes multicast. For example, if you're using solicited, you don't have to send to every device, but you only send to devices that needs that information. Right. Let me not waste much time because I think we'll look at this later on. With Anycast, this in IPv4, we don't have that type of address. Anycast basically is an IPv6 address which is assigned to multiple devices. One address. This one is usually used for servers. Right. So we have a server rimuno Harare. We have a server rim Blawayo. We have a server rikwamtari. Another city munomishi Harare, Blawayo, Mutare, Gweru. I think Gweru is a city, right? Let's say 4 cities are. We have my servers Edu, Ariko Ikoko. Instead of having different IP addresses for all these servers, it comes with some problems. We have same IP address. So if IP address is A up, it's A up, A up, A up. That is what we call an Anycast IPv6 address. The advantage of this IPv6 address is our customers know could IPv6 address to get access to our server is A, whether ari kuBulawayo or ari kwaMutare. So munhu wemuHarare akada kuaccessa server riri muHarare ndo raanosvikira. Munhu ari kuBulawayo akada kuaccessa server anosvikirawo rekuBulawayo. Which server is nearest basically? Ari kwaMutare akashandisa address iyoyo anoreceivawo server rekwaMutare, and it goes like that. Basically, that is what Anycast is. Used